Hello everyone and welcome to this video lecture. My name is Shreya Sangayan, a student at IIPS DAV Indore, enrolled in Dr. Shaligram Prajapat's class on numerical analysis and design. In this video, we will be going through the solutions of three question paper which was assigned by our professor to test our knowledge on the topic. Let's see our first question. In the given question, we have to write an algorithm to accomplish the task for polynomial px given in the following table, where px is equals to an x power n plus an minus 1 x power n minus 1 plus an minus 2 x power n minus 2 plus an minus 3 x power n minus 3 so on plus a1 x plus a0. We have to perform three different tasks for evaluating polynomial px, dividing a polynomial px by x minus r, and find the derivative of polynomial px for iterative approach and recursive approach. Here, there is an algorithm for evaluating the polynomial px using brute force technique, which is also known as iterative approach. Firstly, we have to initialize the sum variable s to 0 for each term of the polynomial from highest to lowest degree. Then, compute the value of the term by multiplying the coefficient with x raised to the degree of the term. Then, add the computed value to the sum variable s, return the value of s as value of the polynomial px. Here's the algorithm for evaluating the polynomial px using recurrence relation, which is also known as recursive approach. If the degree of the polynomial is 0, then return the value of the constant term a0. Otherwise, compute the value of px recursively by computing the value of the polynomial of degree n minus 1 by calling the function recursively. With the polynomial of degree n minus 1 as argument, compute the value of the current term by multiplying the coefficient with x raised to the degree of the term. Then adding the computed value to the polynomial of degree n minus 1. Then return the value of polynomial px. Here is a program for the given algorithm. First, read x and an array A. Initialize the sum as 0 for I is equals to 0 to n in steps of 1. Do read ai. Then n for sum is equals to 0 for I is equals to n to 0 in steps of minus 1, where sum is equals to sum plus ai into a x power I. Then write the sum. Here is the algorithm for evaluating the polynomial using the recursive relation. Here, first we have taken a functional polynomial and initialize as int n, int x, and int array a. If thus n is equals to if n is equals to 0, we have to return a0. Else return an into x power n plus polynomial n minus 1 x int. We have called polynomial as we are using a recursive method. Then we have to read x and an array a. Sum is equals to 0 for I is equals to 0 to n in steps of 1. Then read ai and print polynomial n, x, and array a. Here is algorithm for dividing polynomial px by x minus r. Firstly, we have to initialize the quotient polynomial q and remainder to 0. For each term of the polynomial from highest to lowest degree, compute the value of the current term of quotient by dividing the coefficients by x minus r. Add the computed value to the quotient polynomial q. Then compute the value of the current term of the remainder by multiplying the quotient of the term with x minus r. Subtract the computed value from the current term of polynomial. Then add the computed value to the remainder polynomial r. Then return the quotient q and remainder r. Here, algorithm for computing the derivatives of polynomial px. Initialize the derivative polynomial d to 0. For each term of the polynomial from highest to lowest degree, compute the value of the derivative of the current term by multiplying the coefficient with the degree of the term and subtracting 1 from the degree. Then add the computed value to the derivative polynomial d, return the derivative polynomial d. Here is a program for dividing polynomial px by x minus r. Where firstly we have to read x, n, and array a, r. Initialize sum as 0 for I is equals to 0 to n in the steps of 1 to read AI. And for Q is equals to 0 and R is equals to 0. Here Q is quotient and R is remainder. For I is equals to n to 0 in steps of minus 1. Firstly, CQ is equals to AI divided by x minus R. Q is equals to Q plus CQ into x power I. CR is equals to Q into x minus R. R is equals to R minus AI into x power R minus CR. Writes QR. Here is a program for derivatives of polynomial Px. Here, firstly, we have to read x and a. Initialize sum is equals to 0. For I is equals to 0 to n in steps of 1 to read AI. And for d is equals to 0, here d is equals to derivative of polynomial d. For I is equals to n to 0 in steps of minus 1, cd is equals to ai into n minus 1. Here derivative is equals to d plus cd, right derivative. Now let's see our second question. In our second question, we have to write the algorithm or flowchart of the following task and complete the table. Different tasks are subtraction of n1 minus n2, multiplication of n1 by n2, and division of n1 by n2. So, algorithm for addition is, first we will read n1 and initialize it as m1 comma e1. Then we will read n2 and initialize as m1 comma m2. If e1 is equals to e2, then we will initialize m as m1 plus m2, where e is equals to e1, and store it as a. If the equation is normalized, we will print m comma e and we will stop the program. If the equation is not normalized, then we will normalize by shifting the decimal part for 0, 1 and add for each shift of Mantessa adjust exponent. If the value of exponent is greater than 999, then we will print overflow. If the value of exponent is less than 999, then we will print underflow, and we will other than we will save the value at a. If e1 is not equals to e2, we will check e1 is greater than e2. If e1 is greater than e2, we will shift the mantissa of e2 by difference of mod e1 minus e2, and we will store m as m1 plus m2 dash and e as e1 and print a. If e2 is greater than e1, then we will shift mantissa of e1 by e2 comma e2 minus e1 and m as m1 dash plus m2 and e as e2. Now let us see algorithm for multiplication. We will read n1 as m1 comma e1 and n2 as m2 comma e2. Initialize m1 as m as m1 comma m2 and e as e1 plus e2. If then we will store the value of m and e at a. Then if the equation is normalized, we will print m comma e, and if the equation is not normalized, then we will normalize by shifting decimal part for 0, 1 and n2 for each shift of Mantessa adjacent component. If the exponent value is greater than 999, then we will overflow. If value of expression is under the 99, then we will print underflow. Algorithm for division is, we will read n1 as m1 comma e2 and n2 is equals to m2 comma c2. Initialize m as m1 by m2 and e as mod e1 minus e2. If the equation is normalized, we will print m comma e and stop the program. If the equation is not normalized, we will normalize by shifting decimal part for 0, 1 and n2 for each shift of Mantessa adjacent exponent. If the value of exponent is greater than 999, then we will overflow. If it is not, then we will print underscore. In the given question, we have to verify associative law and distributed law of arithmetic with fitting four Mantis digits and provide correct answer if no number is truncated. The given equations are a plus b minus c is not equals to a minus c plus b, where a is equals to 0.5665 e1, comma b is equals to 0.5556 e minus 1, and c is equals to 0.5644 e1. And second equation is a into b minus c is not equals to ab minus ac, where a is equals to 0.5555 e1 and b is equals to 0.4545 e minus 1 and c is equals to 0.4535 e1. Let's see our case 1. To verify the associative law and distributed law of arithmetic with fitting for Mantis digit, we need to perform the operation on a given value and check if the result satisfies the law. First, we will take the values of a, b and c, where exponents a plus b exponents are not equal. There a is equals to 0.5665 e1 and b is equals to 0.005556 e. Then a plus b is equals to 0.572 e1, and so we will minus 0.572 e1 with 0.5644 e1, which will give us LHS, which is equals to 0.7600 e1. For RHS, we will first take a minus c, which is equals to 0.0021 e1, and here b is equals to 0.556 e minus e1. So a minus c is equals to 0.2100 e minus 1. So a minus c plus b is equals to 0.7656 e minus 1. Therefore, value of LHS is 0.7600 e minus 1 and value of RHS is 0.7656 e minus 1. Therefore, LHS is not equals to RHS. Therefore, A into B plus C is not equals to AB plus AC, and the distributive law also does not hold for this value. Therefore, neither the associative law nor the distributive law holds for this value. Now, let us see our second equation. To verify the associative law of arithmetic with fitting for mantissa, we need to perform operations on a given value and check if the result satisfies the law. Here, LHS value is equal to 0.55 e minus 1 and RHS is equal to 0.500 e minus 1. Similarly, we have solved, therefore, here a into b minus c is not equals to ab minus c, and the distributed law does not hold for this value. Since no law holds for this value, we cannot provide a correct answer without truncation. Now let us see the given statement is true or false. The first statement says that minimize the number of arithmetic operations whenever possible. So it is true, as there are several reasons why it is beneficial to minimize the number of arithmetic operations wherever possible. If first is efficiency, performing arithmetic operation is a computationally expensive process. By minimizing the number of operations required, we can improve the efficiency and reduce the processing time. Second is accuracy. Each arithmetic operations introduce a certain degree of error which can be accumulated over multiple operations. By minimizing the number of operations, we can reduce the overall error and improve the accuracy of the result. Robustness. Arithmetic operations can also lead to numerical instability and divergence, especially when dealing with large number or values. By minimizing the number of operations, we can reduce the risk of numerical instability and make the algorithm more robust. Memory uses. Each arithmetic operation requires storage space in memory. By minimizing the number of operations, we can reduce the memory uses and optimize the use of available resources. Overall, minimizing the number of arithmetic operations can lead to more efficient, accurate, and robust algorithms with lower memory requirements. Therefore, minimize the number of arithmetic operations where possible. So, statement is true. Second statement states that avoid taking the difference of nearly two equal numbers whenever possible by alternate formulation of problems. If it cannot be avoided, then take the difference before doing other operations. So taking the difference of two nearly equations, equal numbers, can lead to the loss of accuracy and numerical instability, especially when dealing with floating point arithmetic. This is because the difference between two nearly equal numbers can result in a very small number that may be lost due to limited precision of floating point arithmetic. For example, consider the subtraction of two nearly equal numbers. So a is equals to 1.1 and b is equals to 1.2. Therefore, c is equals to a minus b. In this case, the value of c is very small and may be lost due to limited precision of floating arithmetic. This can lead in inaccurate result and numerical instability, especially if the c is used in subsequent calculation. To avoid this problem, it is recommended to use an alternative formulation of the problem that avoids taking the difference of two nearly equal numbers. This can involve algebraic manipulation or reordering of calculations to reduce the sensitivity to small changes in the output. If it is not possible to avoid taking the difference of two nearly equal numbers, it is recommended to take the difference before performing other operations. This can help to reduce the impact of loss of precision and improve the accuracy of the result. Overall, avoid taking the difference of two near equal numbers and taking the difference before performing other operations can help to improve the accuracy and numerical stability of algorithm that's involved floating points arithmetic. Therefore, the given statement is true. Third statement states that adding or subtracting numbers starting with the smallest number and work with the number in ascending order. Given statement is true. As when adding or subtracting numbers with different magnitude, it is important to start with the smallest number to reduce the impact of the limited precision of floating points arithmetic. This is because small numbers have fewer digits and are less sensitive to rounding errors than a large number. By working with numbers in ascending order, we can also reduce accumulation of rounding errors and numerical instability. This is because rounding errors accumulate more rapidly when adding or subtracting large numbers, while small numbers are less sensitive to these errors. For example, consider the following calculation. A is equals to 1.23, B is equals to 0.004, C is equals to 45.67, and D is equals to 0.0005. If we add these numbers in a descending order, we get result A plus C plus B plus D, which is equal to 46.9035. However, if we add them in ascending order, we get result is equals to B plus D plus A plus C is equals to 46.9035. In this case, adding the small numbers first reduce the impact of rounding errors and improve the accuracy of the result. Overall, adding or subtracting numbers starting with the smallest number and working with the numbers in ascending order can help to improve the accuracy and numerical stability of the calculation, especially when dealing with floating point arithmetic. Therefore, the given statement is true. Now, let us read our next statement. Do not formulate an algorithm test whether a floating point number equals 0. It is not recommended to formulate an algorithm that tests whether a floating point number equals 0 because floating point numbers are not equal and their values may be subjected to rounding errors. Due to the limited precision of floating point arithmetic, it is difficult to represent certain numbers exactly, including 0. This means that even if two floating points numbers are mathematically equal to 0, their representation in memory may differ due to rounding errors. Instead of testing whether a floating point numbers equal 0, it is better to use a threshold or tolerance value to check whether the absolute value of the number is sufficiently small. This approach is also known as Epsilon test. Here is an example of Epsilon test algorithm in pseudocode. Function is 0, x comma epsilon and return abs x where epsilon is greater than abs x. In this algorithm, x is the floating point number being tested and epsilon is the tolerance value. The abs function is used to get the absolute value of x and the function returns true if the absolute value is less than epsilon, indicating that x is efficiently 0. Using an epsilon test, we can handle floating point number more accurately and robustly than testing for exact equality to 0. In the fifth statement, conditioning of problem is normally due to improper formulation and can be eliminated carefully by reformulating the problem. A practical way, if detected suspected ill conditioning, is to alter the parameters by small amount and observe their effect on the solution. Partially true. The statement is partially true. Ill conditioning of problems can be due to improper formulation, but it can also be due to the nature of the problem itself. Ill conditioning means that small changes in the input or parameters of the problem can lead to large changes in the output or solution. This makes the problem difficult to solve accurately and can lead to numerical instability. One way to detect suspected ill conditioning is indeed to alter the parameters by small amount and observe their effect on the solution. This is known as sensitive analysis. By analyzing the sensitivity of the solution to change in the input parameters, we can determine the problem is well conditioned or ill conditioned. If the solution is highly sensitive to small changes in the input, then the problem is likely to be ill conditioned. However, simply altering the parameters of the small amount may not always be enough to eliminate ill conditioning in some cases. A careful reformulation of problem may be necessary to improve its conditioning. This may involve changing the formulation of the problem, introducing additional constraint or assumption, or using a different numerical methods or algorithm. Therefore, while detecting suspected ill conditioning through sensitivity analysis is useful first step, addressing ill conditioning may require a more thorough analysis and reformulation of the problem. The sixth statement states after a numerical algorithm is obtained, check if it can lead to numerical instability. In such algorithms, error goes in each step of calculation. In such case, reformulate a solution procedure to get a stable numerical algorithm. This statement is partially true, as numerical algorithm can indeed lead to numerical instability, where error goes in each step of calculation. This can be due to variety of factors such as ill-conditioned problem, numerical round of errors, or instability in algorithm itself. To ensure numerical stability, it is important to carefully analyze the algorithm and its implementation to identify potential source of instability. This may involve testing the algorithm on a range of input values. Examining the behavior of algorithm as input values are varied and comparing the result with analytical or exact solutions where possible. If numerical instability is detected, then the solution procedure may need to be reformulated to get a stable numerical algorithm. This may involve using alternative numerical methods or algorithms that are known to be more stable. Modifying the existing algorithm to reduce the impact of numerical errors or round off, or introducing the additional constraints or assumption to improve the conditioning of the problem. Therefore, while checking for numerical instability is an important step in the development of numerical algorithm, addressing instability may require a more through analysis and reformulation of the algorithm to ensure that it's stable and reliable for a range of input values and conditions. The seventh statement states if severe rounding errors and consequent loss of significant digit is anticipated and if no alternate formulation to avoid this is possible, then carry more significant digits in a critical calculation using floating point numbers in double precision mode. In this mode, the length of the mantissa is twice that of other floating point quantities. Statement is true, as severe rounding errors and consequent loss of significant digits can occur in numerical calculation, particularly when dealing with quantities that vary widely in magnitude or when performing operations on values that are close to the limits of machine precision. In such cases, if no alternate formulation is possible, to avoid this loss of precision, carrying more significant digits in critical calculation can help to minimize the impact of rounding errors. One way to achieve this is by using floating point numbers in double precision mode, which allows for twice the number of digits in mantissa compared to standard floating point number. This can help to increase the precision of critical calculation and reduce the potential for rounding errors to affect the accuracy of the final result. However, it is important to note that increasing the precision of the calculation can also increase the computational cost and memory requirements of the algorithm. Therefore, it is important to carefully balance the need of the precision against the computational resources available and to consider alternative methods of formulation where possible to reduce the impact of rounding errors on the final result. Double precision requires large memory and slow down calculation. This is true as double precision requires more memory space than standard single precision, as each double precision floating point number requires 64 bits of memory compared to 32 bits for a single precision number. However, whether or not double precision slow down the calculation depends on the specific context and computational requirements of the algorithm. In some cases, double precision may be necessary to achieve the desired level of accuracy or to avoid numerical instability caused by rounding errors. In this situation, the benefit of increased precision may outweigh the additional memory requirements and computational cost. In the other cases, where lower precision is sufficient or where the computational resources available are limited, it may be more efficient to use single precision floating point number or to consider alternative methods or formulation that reduce the impact of rounding errors on the final result. Ultimately, the choice precision for a numerical algorithm should be based on careful consideration of the trade-off between accuracy, computational efficiency, and memory requirements, taking into account the specific context and goals of the problem being solved. In the third iteration of the finding square root of 5 with standard 0.7 using Newton-Raphson method, relative error is 0.0013. So, based on the given information, we can make an assumption that the formula used to find the square root of 5 is xn plus 1 is equal to 0.5 xn plus 5 by xn, where xn is the nth approximation and x comma n plus 1 is the n plus 1 approximation. We can estimate the value of x3 third iteration as follows. So, x0 is equal to 7, x1 is equal to 0.5 into 7 plus 5 by 7, which is equal to 3.07143, and x2 is equal to 0.5 into 3.07143 plus 5 by 3.07143, which is equal to 2.23868. Now assuming that the relative error is defined as as xn plus 1 minus xn by xn plus 1. We can calculate the relative error between x2 and x3. Relative error is equal to x3 minus x2, which is equal to 0.0013. So, therefore, the third approximation of square root of 5 using a Newton-Raphson method with starting point 7 and relative error of the approximation is 0.003 is approximately 2.244119. The iterative methods are compared on the following parameters: the rate of conversion, the amount of computational efforts per iteration, sensitivity of the methods to starting value and intermediate value. Yes, rate of convergence refers to how quickly the iterative method converges to the desired solution. The faster the rate of convergence, the better the method. Amount of computational efforts per iteration. It refers to the amount of computation required to obtain the next approximation in the iterative process. A method that requires less computational efforts per iteration is performed. Therefore, the given statement is true. Now, let's understand what is interpolation. Interpolation is a technique of estimating the value of a function for any intermediate value of independent variables. While the process of computing the value of the function outside the given range is called extrapolation. The different ways of interpolation are Newton's Grigori forward interpolation formula. This formula is particularly used for interpolating the values of fx near the beginning of the set of the given. H is called the interval of difference and u is equals to x minus a by a, where a is the first term. Second, Newton's Grigori backward interpolation formula. This formula is useful when the value of fx is required near the end of the table. H is called the interval of difference and u is equals to x minus an by h. Here an is the last term. Lagrange's interpolation formula. Lagrange's interpolation formula finds a polynomial called Lagrange formula that takes on certain values at an arbitrary point. It is an nth degree of polynomial expressions to the function fx. The interpolation method is used to find the new data points within the range of the discrete sets known as data points. Here, Lagrange's interpolation formula is fx is equals to x minus x1 into x minus x2 till so on till x minus xn by x0 minus x1 into x0 minus x2 so on into y0 plus x minus x0 into x minus x2 by x1 minus x0 into x1 minus x2 till yn. Fourth is Newton divided difference interpolation formula. It is an interpolation technique used when the interval difference is not same for all sequence of values. Suppose f0, fx, fx be the n plus 1 value of the function y is equals to fx. Corresponding to the arguments x0 is equals to x0, x1, x2, so on xn. Where interval difference are not same, then the first divided difference is given by x0 by x1 is equals to fx1 minus fx0 upon x1 minus x0. Simpson's one-third rule states that sim is an extension for the trapezoidal rule in which the integrated integrand is approximated by second-order polynomial. Simpson rule can be derived from the various ways using Newton divided difference polynomial, Lagrange's polynomial, and method of coefficient. Simpson's one-third rule is defined by integral f x dx a to b is equals to h by 3 y0 plus yn plus 4 y1 plus y3 plus y5 till y minus n minus 1 plus 2 y2 plus y4 plus y6 plus yn minus 2. This rule is known as Simpson's one-third rule. Simpson's 3 by 8 rule is another method of numerical integration is called Simpson's 3 by 8 rule. It is completely based on a cubic interpolation rather than quadratic interpolation. Simpson's 3 by 8 or 3 by 8 rule is given by integral fx dx a to b is equals to 3h by 8 y0 plus yn 3y1 plus y2 plus y4 plus y5 so on till y plus yn minus 1 plus 2 y3 plus y6 till yn minus 3. This rule is more accurate than the standard method as it is used for more functional value for 3 by 8 rule. The composite Simpson's 3 by 8 rule also exists, which is similar to generalized form. The 3 by 8 rule is also known as Simpson's second rule of integration. Now let's solve our second internal question. In this paper, the first question was, which of the following interpolation techniques is used to find the values of a function at points lying outside the known data points? First option is Newton forward interpolation, Newton forward backward interpolation, Newton divided difference interpolation, and Lagrange's interpolation. So the right answer is Newton divided difference interpolation. Second question was, which of the following is not a disadvantage of the Newton forward interpolation? So given options are, it cannot be used for large values of n, it requires equally spaced data points, it is sensitive to errors in the data points, it is computationally insensitive. The correct option is it is computationally insensitive. Third question was, which of the following interpolation technique is used to find the values of a function at points lying before the known data points? The given options are Newton forward interpolation, Newton backward interpolation, Newton divided interpolation, Lagrange's interpolation. So the correct answer is Newton backward interpolation. Fourth question is, which of the following interpolation technique uses a polynomial of degree n minus 1 to interpolate n data points? So the given options are Newton forward interpolation, Newton backward interpolation, Newton divided difference interpolation, Lagrange's interpolation. So the correct answer is Lagrange's interpolation. Question 5 states, which of the following is not a disadvantage of Newton backward interpolation? Given options are, it requires equally spaced data points, it is sensitive to errors in the data points, it can not be used for large values of n, and it is computationally insensitive. So the correct answer option is, it cannot be used for large values of n. Which of the following interpolation technique is used to find the values of a function at a point lying between the known data points? Options are Newton forward interpolation, Newton backward interpolation, Newton divided difference interpolation, Lagrange's interpolation. So the correct option is Lagrange's interpolation. Seventh question is which of the following is the correct formula for Newton divided difference interpolation? The given option, the correct option is A, which is fx is equals to fx0 plus fx0 comma x1 plus fx0 comma x1 comma x2 x minus 1 so on. Question 8 states which of the following is the correct formula for the first divided difference in Newton divided difference interpolation. So options are fxi is equals to fxi. So the correct option is fxi is equals to fxi minus 1 by xi minus xi minus 1. Ninth question is what is the difference between a Newton forward and backward interpolation? So options are Newton forward interpolation uses forward difference whereas backward interpolation uses backward difference. Second is Newton forward interpolation uses backward difference whereas Newton backward interpolation uses forward differences. Both Newton forward and backward interpolation method use the same formula for interpolation. D. None of the above. So the correct option is Newton forward interpolation uses forward difference whereas backward interpolation uses backward difference. 10th question is in Newton's divided difference formula, what is the purpose of using higher order differences? To increase the accuracy of interpolation, to decrease the accuracy of interpolation, to make the interpolation faster, none of the above. So the correct option is to increase the accuracy of interpolation. 11th question is which of the following interpolation method is not based on a polynomial approximation? The correct answer is divided difference interpolation as it is not based on a polynomial approximation. Question 12 is what is the difference between Newton divided difference interpolation and Lagrange's interpolation? Given options are Newton divided difference interpolation uses forward differences whereas Newton Lagrange's interpolation uses backward differences. Newton divided difference interpolation uses backward differences whereas Lagrange's interpolation uses forward differences. C. Newton's divided difference interpolation uses divided difference whereas Lagrange's interpolation uses polynomial interpolation. So the correct option is C. Newton divided difference interpolation uses difference whereas Lagrange's interpolation uses polynomial interpolation. In 13th question, which of the following interpolation method is more suitable for uneven space data points? So options are Newton forward interpolation, Newton backward interpolation, divided difference interpolation, Lagrange's interpolation. So the correct option is Lagrange's interpolation. Which of the following interpolation method is known as the method of finite differences? So options are Newton's forward interpolation, Newton's backward interpolation, divided difference interpolation, Lagrange's interpolation. Correct option is divided difference interpolation. 15th question is what is the order of polynomial used in Newton forward interpolation? So options are n, n minus 1, n plus 1, 2n. Correct options is n minus 1. 16th question is which of the following interpolation method uses the concept of interpolation error? Options are A. Newton forward interpolation, Newton backward interpolation, Lagrange's interpolation, none of the above. Correct option is C. Lagrange's interpolation. 17th question is which of the following interpolation method can be used to interpolate functions with complex value? A. Newton forward interpolation, B. Newton backward interpolation, C. Divided difference interpolation, D. Lagrange's interpolation. The correct option is Lagrange's interpolation. 18th. What is the drawback of using higher order differences in Newton divided difference interpolation? A. Higher computational complexity, B. Decreased accuracy, C. Higher degree of polynomial approximation, D. None of the above. So correct option is A. Higher computational complexity. 19th question is what is the difference between a Newton codes formula and Gaussian quadrature formula for numerical integration? Options are Newton codes formula uses equidistant points whereas Gaussian quadrature formula uses non-equidistant points. B. Newton-Cotes formula use non-equidistant points, whereas Gaussian quadrature formula uses equidistant points. Both Newton-Cotes and Gaussian quadrant formula use the same types of point for integration. Answer is Newton-Cotes formula use equidistant points, whereas Gaussian quadrature formula use non-equidistant points. Question D is which of the following is an example of Newton-Cotes formula for numerical integration? A. Simpson's one-third rule, Simpson's 3/8 rule, trapezoidal rule, both A and C. So answer is Simpson's 3/8 rule. 21st question is which of the following is an example of Gaussian quadrature formula for numerical integration? A. Trapezoidal rule, B. Simpson's one-third rule, C. Simpson's 3/8 rule, and D. Gauss-Legendre quadrature. So the correct option is D. 22nd question is which of the following is true regarding the weights and abacus used in Gaussian formula? A. The weights and abacus are equal in number. B. The weights and abacus are not equal in number. C. The weights and abscias are same for all order of formula. So the correct answer is A. The weights and abscias are equal in number. The next question is what is the order of the accuracy for Simpson's 3/8? So options are A1, B2, C3, D4. So the correct option is C3. Next question is which of the following is an example of a composite integration method? Trapezoidal rule, Simpson's 1/3 rule, both A and B. So the correct option is both A and B. Question number 25 is what is the drawback of using higher order Newton-Cotes formula for numerical integration? So options are they are less accurate than lower order formulas, they are required more functions evaluation, C they are not applicable to non-smooth functions. So the correct option is B they required more functions evaluation. Question number 26 is which of the following is true regarding the abscias used in Gauss-Legendre quadrature. So options are they are equidistant, they are non-equidistant, they are dependent on order of formula. So correct option is they are equidistant. Which of the following is an example of an open Cotes formula? Options are A. Trapezoidal rule, B. Simpson's 1/3 rule, C. Simpson's 3/8 rule, both B and C. So correct option is D, both B and C. Question number 28 is what is the forward difference operator? A. It approximates the derivative of function using the value of the function at two neighbor points. B. It approximates the derivative of a function using the values of the function at three neighboring points. C. It approximates the derivative of function using the value of the function at four neighboring points. D. None of the above. So the correct option is A. It approximates the derivative of a function using the value of function at two neighboring points. Question number 29 is what is the backward difference operator? A. It approximates the derivative of a function using the values of the function at two neighboring points. B. It approximates the derivative of a function using the value of the function at three neighboring points. C. It approximates the derivative of a function using the value of the function at four neighboring points. D. None of the above. So the correct option is it approximates the derivative of a function using the value of the function at two neighboring points. 38th question is what is the difference divided difference operator? A. It is used to approximate the derivative of a function at a given point. It is used to interpole a function at a given point. C. It is used to approximate the derivative of a function using the value of the function at multiple neighbor points. So the correct option is it is used to approximate the derivative of a function using the value of the function at multiple neighboring points. Question number 31 is what is shift operator? Shift operators it shifts the value of a function to left or right. It approximates the derivative of a function using the value of the function at a multiple neighboring points. C. It is used to interpolate a function at a given point. D. None of the above. So the correct option is A. What is the order of the accuracy for the Simpson third rule, which is 2? Question number 33. Which of the numerical integration method is based on the use of the forward distal operator. So options are trapezial rule, Simpson's rule, midpoint rule, none of the above. So both A, B, C are not the correct answer. Correct option is none of the above. 34th question is which of the following numerical integration method is based on the use of the backward difference operator? Options are A. Trapezial rule, Simpson's rule, midpoint rule, none of the above. So the correct option is none of the above. Question 35th is which of the following numerical integration method is based on the use of the central difference operator? A. Trapezial rule, B. Simpson's rule, C. Midpoint rule, D. None of the above. So correct option is D. None of the above. Question number 36 is which of the following numerical interpolation formula is based on the use of the divided difference operator? Options are A. Newton divided difference formula, B. Lagrange's interpolation formula, C. Hermite's interpolation formula, D. None of the above. So the correct option is Newton's divided difference formula. Question number 37 is which of the following numerical interpolation formula uses polynomial interpolation? Answers is A. Newton's divided difference formula, B. Lagrange's interpolation formula, C. Hermite's interpolation formula, D. None of the above. So the correct option is B. Lagrange's interpolation formula. Question number 38 is which of the following numerical interpolation formula is used for interpolating a function with both its value and derivatives at a given point? So correct option is C. Hermite's interpolation formula. Question number 39 is which of the following is true for numerical integration method based on the higher order polynomial? Options are they are more accurate than those on lower order polynomials. They are less accurate than those based on a lower order polynomials. See, they are equal accurate as those based on a lower polynomial. So the correct option is A. They are more accurate than those based on lower order polynomial. Question number 40 is Jacobi's method is also known as displacement method, simultaneous displacement methods, simultaneous method, B. Diagonal method. So the correct option is B. Simultaneous displacement method.